Okay, so here I have a series RLC circuit. We are given the source voltage, a capacitance, an inductance, and a resistor, and we're supposed to find the angular frequency for which the imaginary part of the impedance is equal to 0. Well, you probably maybe already know the answer to this, but in case you don't, we'll show it again. So we have a voltage source, which would be 10 angle 0. It's series, so we have a resistor, a capacitor, and an inductor. And the resistor is 500 ohms, and the capacitor is minus J over omega C, and the inductor is J omega L. And so in order for the imaginary part to be 0, minus J over omega C plus J omega L has to equal 0. So that means J omega L has to equal J over omega C. Or I can cancel out the J's and multiply both sides by omega, and I get omega squared L equals 1 over C. Divide both sides by L, omega squared equals 1 over LC, and omega equals the square root of 1 over LC. Does that look familiar? Yes. Because it said find the part where the imaginary part equals 0. I'm not finding the total impedance, just the imaginary part, and the resistor is real. The resistor is just 500. And so I could write it in there, but then I'd immediately take it out because that's not the part I'm looking at. And so does anyone know another name for this frequency we just found?
Resonant frequency?
That's the resonant frequency. And it turns out you would get the same answer whether this was a series or a parallel RLC circuit. It's 1 over this, omega equals 1 over the square root of 1 over LC. So anytime you are told it's at the resonant frequency, you know that resonant frequency is the square root of 1 over LC, and you know that the imaginary part of the impedance is 0. So knowing that, what is the total impedance of this circuit if we are at this frequency? So at resonant frequency, Z equals, well, we know that Z equals 500 plus minus J over omega times, the capacitance was 200 microfarads, 200 times 10 to the negative 6, plus J omega times, the inductor is 200 millihenries, so 0.200. But, and we know that omega is the square root of 1 over L is 0.2 times 200 times 10 to the negative 6. Can someone do this for me real quick and tell me what this frequency is? I'm getting, my answer tells me it's 158.11. And units, if you had to put units on this, is radians per second. Okay, so then I would plug that in, and if I did that, I would get 500. and I didn't just do all that in my head. I know that at the resonant frequency, the imaginary part of the impedance is 0. So that means my capacitor and my inductors add together to be 0, and all I have are my resistors. So if you are at resonant frequency, you just have the real part of the impedance. That can save you a lot of time on doing calculations. You don't have to plug all that stuff in. The total impedance is just going to be the resistance. Okay, so we could calculate all this, but we would get 500. And so now, with the other part of the problem says, find the current and the voltages for the frequency found in part A. So the current, V equals I times Z, and V was 10 equals I times 500. So I equals 10 over 500, and unless I'm mistaken, I think that's 0.02 angle 0. I think that's right. And then to find the voltages, now that I know it's 0.2, I would just multiply each of the impedances by the current. So I'm not going to do that. 'Cause that's, yes.
And so how do you determine this resonant frequency at a certain time?
In this problem, it's because it said find the angular frequency for which the imaginary part of the impedance is equal to 0. So that's equivalent to saying that you are at resonant frequency.
Whatever it says Z is equal to 0.
Not Z is equal to 0, the imaginary part is equal to 0. So what is the name of the imaginary part of the impedance? Reactance. Reactance. So this is equivalent also to saying the reactance equals 0. No, that's resistance. Yeah. Yes.
And if omega is not given to you like the first problem, you would solve it. How would you do it?
The reason we solved for it here is because it asked us to find it. It said find the angular frequency. If they didn't tell us that, and they just said you are at the frequency that makes it equal to 0, you don't need to find it, because you know at that point the frequency doesn't matter, because it's only the resistance that's going to play a role, and the frequency doesn't matter for that.
Whenever I was like looking at videos of it, I didn't understand it properly, and I think I saw somewhere, you might have talked about this, but I think I saw somewhere like at resonant frequency, like a parallel inductor capacitor is like a big open circuit. True?
So at resonant frequency, a parallel, yes,
And then if they're in series, it'd be like a short. Right?
yes,
Okay.
yes.
So can you like kind of cheat and use that to find values? If like you have a circuit that he gives you and he tells you, yeah, it's at resonance, then can I kind of cheat and be like, well, if it's at resonance, then I'm just gonna call this a big open and call this a short, and then
Yes, that does work.
and then I've got current, I've got voltages.
Yes,
Okay.
yes. So if it's at resonant frequency, then you can use all of those kinds of shortcuts.
Okay. Cool.
Yeah.
Parallels open and series short.
Yeah, and that makes sense, because what we're saying is if we had parallel,
They like cancel each other out in their effects.
the imaginary part is supposed to be equal to 0. So this part is open.
So it would just be syncing through the resistance.
And then if they're in series, they also cancel each other out, and that makes this like a short circuit.
Okay. Cool. So you got cheat. Okay.
Yep. Okay, other questions about resonant frequency? All right, yes.
So when they're all in parallel like that, would it still just be the resistance, or would that be zero?
It would be. It would just be the resistance. With this part, like he was just saying, you treat this part like it's open. Like,
Okay.
yeah, yeah.
You can still plug through this.
It's still, it is going to go through the resistor. Yeah. Yeah. And I was getting myself into trouble with this earlier because I was trying to say, well, if this is 0, and let me do product over sum to do parallel, but that doesn't work if you have that. So instead, it's best just to think of it like we were talking about with like this part acting like as a short. Okay, I'm going to go ahead and let's see. I'm just not going to, I'm going to do the next problem on the same recording to save time. And I'm going to do problem number 6, I think. I think 6 gets us the most bang for our buck, although probably we'll skip doing some calculations just to save time. So if you want to know how to do it on your calculator in the easiest way possible, I'll let you know because I have to figure out the easiest way or else I'm going to mess it up. Yeah.
So like this is kind of like on topic, but like in here, whenever we talk about resonant frequencies and stuff like that, all of our values, like ideal and exact. But in real life, is it even actually like possible to get like a resonant frequency with these circuits since like all your components vary widely?
Yeah, you can. And it's as long as it's like it'll display the conditions, the features of being in resonance. As long as it's within a close enough window. So yeah, you can.
If not, you might just not be affected with that.
Right. Okay, so for this one, we are supposed to find the AC voltage across the resistor capacitor parallel combination, and we're supposed to use the source transformation method. So let's change everything to phasors. So we'll have our voltage source will be 10 volts, 10 angle 0. Our resistor R1 is going to be just 500 ohms. Our inductor, which was 15 millihenries, is going to be J omega 0.015. Our second resistor is going to be 1500. Our capacitor is going to be minus J over omega and it was 20 nanofarads, so 20 times 10 to the negative 9. And then we have a current source that was given to be 14.14 milliamps at an angle of negative 45 degrees. So that would be 0.014 angle negative 45 degrees. So let's put these together. So that's 10 angle 0. And I'll put these together and call them Z1. And then I will take these two and put them together and call them Z2. And then I have my current source over here, which was 0.14 angle negative 45. So Z1 would equal 500 plus omega is given as 33.33 kiloradians per second. So that turns out to be, if I add these together, 707.1, well, 500, it turns out to be 500 plus J 500, which is 707.1 angle 45 degrees. And Z2 is R2, which is 1500 times minus J over omega, which was 33,333 times 20 times 10 to the negative 9 over 1500 plus negative J over 33333 times 20 times 10 to the negative 9. And if you do all that, you get 1500 over 1 plus J, which ends up being 750 minus J 750, which is 1060 angle negative 45 degrees. I forgot what we were looking for. We're looking for the AC voltage across the resistor capacitor. So we're looking for the voltage across Z2. And it says to use source transformation. So we have not source transformed yet. What would we need to source? How could we do a source transformation that would help us out here? What kind of source transformation could we do? We don't want to do that, because we could change the current source to a voltage source, but then we're transforming Z2. And we're supposed to be finding the voltage across Z2. You never want to transform the thing that you're looking at. So that only leaves us another thing to transform, is the other side. So we want to transform. So what we have a voltage source and an impedance. And we have an impedance in parallel with a current source. So we could, and ordinarily that's what I would do, is I would transform the current source, because I hate current sources, hate them. But we can't do that because the problem is asking for us to find the voltage across the resistor, capacitor, parallel combination, which is Z2. So we have to transform these two. And the way you do that is to transform a voltage source and an impedance in series. That's going to transform to a current source and an impedance in parallel. So the impedance doesn't change. The current becomes the voltage over the impedance. Well, that's handy because if you remember, our current source was angle negative 45. It was 0.014 angle negative 45. And what was Z1? We computed it, didn't we?
77.1.
Yeah. So if we take 10 over 707 angle 45, what's our new angle going to be? I can't do 10 over 707 in my head, but I know what my angle is going to be. Negative 45. And that's good because we don't really know how to deal with a circuit that has two different, well, yeah, we do. We could deal with that. But 10 over 7.7 is 0.01, no. Yeah, it is 0.014. So now I have two current sources that are identical. And what has to be true about the voltage across Z1 and the voltage across Z2? They have to be equal because they're in parallel. And it would equal, the only thing I can do is to, now I can, so I said before I don't want to transform Z2. But now I'm going to say, well, but it's okay to do simplification and do product over sum. Why would that be okay to do here on this step when I said you don't want to transform it? But I'm saying, yeah, but it's okay to say we can do this. Where I'd have Z1, Z2 over Z1 plus Z2 and find the voltage across that. Why is that okay? It's the same voltage. They're all in parallel, so it has to be the same. So I could find that, and then what would the current be? What would the current be going down this branch right there? Just from KCL, the current coming in here and the current coming in here has to be the current going down there. And so the voltage that we're looking for is going to be 0.014 angle negative 45 times 2, because I have two of them, times my impedance, which would be Z1, Z2 over Z1 plus Z2. And I believe if you do all of those calculations, you would get 16.6 angle negative 33.7. And I have to stop here. But are there questions? I know I didn't do all the calculations there, but I did go over the concepts. Any questions on any of that? Everybody feel good about it? Yeah?
Okay.
Yeah? All right. Well, let me stop this recording. And I will upload these